Welcome back to Three Inquisitive Kids. In this video, we are going to learn how to solve congruences using inverses and the Chinese remainder theorem. Solving congruences is a big part of modular arithmetic. And when we are met with systems of congruences that often look like this, we need to be able to know how to solve them. So let's go over the two steps. For example, if you have something that looks like 2x is congruent to 9, let's say mod 11. Say this is something you wanted to solve. The first step is always to isolate the variable, just like you would if you were solving linear equations. We are going to multiply both sides using the inverse of that constant that is being multiplied to the variable right now. So what is the inverse? Well, the inverse is just written as a to the power of negative 1. Well, it's not called a to the power of negative 1, but that's just the way it's written. So this one right here would be the inverse of a. And we know that because any number times its inverse is always going to be congruent to 1 for a certain modulus. If you guys would like to, we could certainly put up another video talking all about how to find modular inverses. Now that we have isolated the variable, the second step is to apply the Chinese remainder theorem. So now that you have isolated all the variables, and the one variable is on the left side with multiple remainders and moduluses, all you have to do is solve. Now the Chinese remainder theorem is a specific series of steps that allows you to solve for x. Basically, you have 6 values, a1, a2, a3, and m1, m2, m3. Big M is just the product of all the small m's. And now, after knowing big M, we can find big M1, big M2, big M3, so on. Big M1 is equal to big M divided by small m1. Big M2 is equal to m divided by small m2. And big M3 is equal to big M divided by small m3. Now we use these values to plug into the formula. So to find x, we're just going to multiply a1 with m1 with the inverse of m1 plus a2, m2, and the inverse of m2, so on, depending on how many equations you have. And finally, we're going to take the modulus big M. And that is how we're going to find our final answer. And that is the solution of using the Chinese remainder theorem to solve a system of congruences. Let's look at our first example. Usually you understand it better if you see the steps in action. Here we have two congruences. 6x is congruent to 4 modulus 11, and 4x is congruent to 6 mod 7. The first step is to isolate the variable by multiplying the inverse on both sides. Let's start with 6x is congruent to 4 mod 11. As you can see, we have to multiply the inverse of 6 on both sides here, the modular inverse. How do we find the modular inverse? 6 times its inverse, let's call it a, is going to be congruent to 1 modulus 11. What number can we multiply to 6 to make that value have a remainder of 1 when divided by 11? Well, if we add 11 to 1, that's 12, 23, 34, so on. But as you can see, we already have a multiple of 6, meaning that 6 times 2 is congruent to 1 mod 11. This is true, which means that 2 is a. So 2 is the modulus inverse of 6 in this case. That means we can multiply 2 onto both sides, and that gives us x is congruent to 8 mod 11. That's the first part of our rewritten equation. Now let's do the same thing for 4x is congruent to 6. 4x is congruent to 6. Mod 7. Well, to find, let's write a again as 4's modular inverse. 4 times a, so 4 times a number, is congruent to 1 when divided by 7. So this number will have a remainder of 1 when divided by 7. Let's start by adding 7 to 1, which is 8, then 15, 22, so on. As you can see, we already see a multiple of 4, which means that a is equal to 2. We can multiply 2 onto both sides of this equation, giving us x is congruent to 12 mod 7. By multiplying the inverse onto both sides of the congruences, we have isolated the variable on the left side. Now it's time for us to use the Chinese remainder theorem to solve this system of congruences. All we have to do now is follow these steps. Let's first identify all our variable values here. What is a1? Well, here we have a1 and a2, and they are respectively 8 and 12. We also know m1 and m2, which is 11 and 7. And here we have big M. So big M is just multiplying the two small m's together. So big M is equal to 77. Big M1 is just 77 divided by small m1, which is 7, and big M2 is equal to 11. Now all we have to do is find the inverses of these two respective values. We can do that by substituting the values of big M1 and 2. For example, big M1 is 7, so 7 times its inverse is going to be congruent to 1 mod 11, because that's the 11 from up here. So now let's try to see what value would make this true. Let's keep adding on 11 to 1. So we have 12, 23, 34, 45, 56. So 56 is a multiple of 7, which means that the inverse of big M1 would be 8. Now the same steps for the inverse of big M2. 11 times the inverse of big M2 is going to be congruent to 1 mod 7. Let's keep on adding 7 to see if there will be a multiple of 11. We'll get 8, 15, 22. 22 is the second multiple of 11, which means the inverse of big M2 is equal to 2. Now that we have all our basic variables down, let's substitute them into this equation right here. To find x, all we have to do is x is equal to 8 times 7 times 8 plus 12 times 11 times 2 mod the big M, which is 77. So let's simplify this. X would be equal to 712 mod 77. And of course, that would be the same as x is equal to 19 mod 77. So in the end, this is our final answer. Now moving on to example number 2. And here are the word problems. So we have an extra step, which is writing out the equations for ourselves. Lily has more than 11 marbles. When she puts them into groups of 7, there is 1 marble left. When she puts them into groups of 4, there are 2 marbles left. What is the smallest possible number of marbles that Lily has? Let's start by writing the system of congruences. So let's set the variable, the smallest possible number of marbles, as x. X is greater than 111. X is congruent to 1 mod 7. X is congruent to 2 mod 4. So this is the system of congruences that we are being asked to solve. Lucky for us, x is already isolated, so all we have to do is just apply the Chinese remainder theorem. Pause the video to see if you can use the steps from the previous example to help you solve this example. Well, we always start off by identifying our values. A1 is equal to 1, A2 is equal to 2, small m1 is equal to 7, and small m2 is equal to 4, meaning that big M is equal to the product of 7 and 4, which is 28. So this also consequently gives us big M1 is equal to 4, and big M2 is equal to 7. Finally, we have to find the inverses. So what are the inverses of big M1 and big M2? Well, all we have to do is plug in the values of big M1, right? 4 times the inverse of big M1 is congruent to 1 when mod 7. So let's start by adding 7 to 1. We have 8, 15, so on. But 8 is already a multiple of 4. 4 times 2 is equal to 8. So 2 would be the inverse of big M1. Now we're going to do the same for the inverse of big M2. 7 times the inverse of big M2 would be congruent to 1 mod 4. Let's start by adding 4 to 1. We'll have 5, 9, 13, 17, 21. And this is a multiple of 7. And 7 times 3 is equal to 21, which means that the value for the inverse of big M2 would be 3. Now that we have all of our values down, the only thing left is to substitute. X is equal to A1 times big M1 times the inverse of big M1 plus A2 times big M2 times the inverse of big M2 mod big M, which is 28. Now all we have to do is simplify. X would then be equal to, this is 8, and this is 42. So 50 mod 28. Or we could rewrite it as 22 mod 28. They're the same thing. So this is our solution here for X. But the question is asking, what is the smallest possible number of marbles that Lily has? So we're looking for the smallest possible number. And X must be greater than 111. So all we have to do is add a certain amount of 28s to 22 to make it greater than 111. So 28k must be greater than 89. K, with itself having to be an integer, must be greater than or equal to 4. So since the smallest possible value for k is 4, substituting back in here, we'll have 22 plus 28 times 4, which is equal to 22 plus 112, which is equal to 134. So in the end, 134 marbles would be the answer. Now let's take a look at our final problem. Example 3. Todd, Eileen, Jane, and Eric decide to go to a haunted house for Halloween. Todd, who is deathly scared of ghosts, asks Eileen, Jane, and Eric to go through the haunted house before him and count all the ghosts they see. Eileen, Jane, and Eric agree to this, but they decided to play a trick on Todd. They come up with this plan. Eileen will count the ghosts by 3s, Jane will count the ghosts by 5s, and Eric will count the ghosts by 19s. After getting through the haunted house, they come back to Todd, and they say, Eileen says, I counted the ghosts by 3s and there were 2 left over. Jane says, I counted the ghosts by 5s and there were 3 left over. Eric says, I counted the ghosts by 19s and there were 7 left over. What is the smallest number of ghosts Todd should be prepared for? So yet again, this is another word problem, which means we have to write the system of congruences for ourselves. But it is already pretty clear. We have 3 congruences. So let's set the smallest number as x. X is congruent to 2 mod 3. X is congruent to 3 mod 5. And finally, x is congruent to 7 mod 19. Great for us, we don't have to multiply any inverses because the variable is already on its own. All we have to do is use the Chinese remainder theorem. And here there are 3 congruences, which means there are a couple of extra steps, but the logistics are still the same. Let's use the steps of the Chinese remainder theorem to help us out here. Let's start by identifying our values. A1 is equal to 2, A2 is equal to 3, A3 is equal to 7. Small m1 is equal to 3, small m2 is equal to 5, small m3 is equal to 19, meaning that big M is equal to their product. 3 times 5 times 19 is 285. So what is big M1, big M2, and big M3? Big M1 would be 285 divided by 3, which is equal to 95. Big M2 would be equal to 285 divided by 5, which is 57. Big M3 would be equal to 285 divided by 19, which is 15. Finally, we have to find their inverses. Let's start with big M1. 95 times the inverse of big M1 is congruent to 1 mod 3. Well, let's see what is the remainder when 95 itself is divided by 3. When 95 is divided by 3, that is 31 remainder 2. The next multiple of 95, 190 divided by 3, gives us 63 remainder 1. This is our first remainder 1, which means that the value of the inverse of big M1 would be 2, because 2 times 95 is equal to 190. Now let's do this for the inverse of big M2. 57 times the inverse of big M2 would be congruent to 1 mod 5. 57 itself divided by 5 would give us 11 remainder 2. 114 divided by 5 would give us a remainder of 4. And 171 divided by 5 would give us a remainder of 1, which means that 3 would be the value of the inverse of big M2. Finally, we do the same thing for the inverse of big M3. 15 times the inverse of big M3 is congruent to 1 mod 19. Adding on 19 to 1, we have 20, 39, 58, 77, 96, 105. And 105 is indeed a multiple of 15. And 15 times 7 is equal to 105. So the value of the inverse of big M3 would be equal to 7. Finally, we have all of our values down. Now we substitute. So x is equal to a1 times big M1 times the inverse of big M1 plus a2 times big M2 times the inverse of big M2 plus a3 times big M3 times the inverse of big M3 mod 285. After simplifying, we have 83 mod 285. Revisiting the question, we see that it's asking for the smallest number of ghosts that Todd should be prepared for. So what is the smallest number of ghosts that he should be prepared for? Adding 83 and 285 together, we have 368. So the final answer would be 368 ghosts. That is the minimum value of x that will make this true. And if you want, you could go back and verify it. Thank you so much for watching through Inquisitive Kids. By the end of watching this video, you now know how to use the Chinese remainder theorem to solve congruences.